It is 1943, at the General Motors Milford Proving Ground in Michigan, the same banked oval test track where Buick had spent years measuring the top speed of its passenger cars. On the track this day is not a passenger car. It is a 20-ton armored vehicle, low and lean and roofless, with a long-barreled cannon poking out over its front. A test driver takes it onto the banked oval, the same banking that Buick used to wind out its sedans, and he opens the throttle. The radial engine in the rear builds to a scream. The automatic transmission shifts itself up through its gears without the driver touching a clutch, and the armored vehicle accelerates down the straight and into the banking, faster and faster, until the needle on the test equipment reads a number that no armored fighting vehicle in the world had ever reached. On the banked track, fitted with special tracks, the vehicle touches 74 miles per hour. In normal service trim, governed for durability, it will do 55. Either way, it is the fastest tracked armored vehicle on Earth, faster than anything the Germans have, faster than anything the British or the Soviets have, faster, in fact, than the M1 Abrams main battle tank that the United States Army will field 4 decades later. The vehicle is the M18, and Buick will call it the Hellcat. And here's the thing that the popular history never quite explains, the thing that one viewer of these stories rightly complained about, the thing that separates a real engineering account from a patriotic recitation. It is easy to say that the Hellcat was fast. It is easy to say that it had an automatic transmission. But how did it actually work? How does a transmission shift itself with no clutch and no driver input in 1943, when the automatic transmission was a technology only 3 years old? How does a 20-ton vehicle reach 55 miles per hour on tracks? Why did this vehicle use a completely different kind of automatic transmission from the one in the Cadillac-powered light tank? And what was the difference, mechanically, between them? These are the questions worth answering, because the answers are where the real engineering lives. This is the story of the fastest armored vehicle of the war, and it is, more than that, the story of exactly how Buick made it go. To understand the Hellcat, you have to understand the strange and controversial military idea that produced it, the idea of the tank destroyer. When the German panzer divisions tore through France in 1940, the United States Army was horrified by the apparent unstoppability of massed enemy armor, and it cast about for a doctrine to defeat it. The answer it settled on, largely the work of General Leslie McNair, was the tank destroyer concept. The idea was that you did not stop a tank attack with your own tanks. Instead, you held your tanks back for offensive exploitation, and you defeated the enemy's tank thrusts with specialized vehicles, the tank destroyers, that were fast, carried a powerful gun, and were held in reserve, ready to rush to wherever the enemy armor was breaking through. The tank destroyer doctrine was summed up in the slogan painted on the tank destroyer insignia, a snarling wildcat crushing a tank in its jaws: seek, strike, destroy. The doctrine demanded a particular kind of vehicle. The tank destroyer did not need heavy armor because it was not supposed to slug it out with enemy tanks in a stand-up fight. Instead, it was supposed to use speed and mobility to rush to the threatened point, to engage the enemy from ambush or from the flank, to use its powerful gun to kill enemy tanks quickly, and then to displace before the enemy could bring its heavier armor and firepower to bear. Speed was the armor. The vehicle would survive not by absorbing hits, but by avoiding them, by being too fast and too nimble to be pinned down and destroyed. This was a controversial doctrine, and after the war, many concluded it had been fundamentally flawed because enemy tanks rarely cooperated by attacking in neat masses that the tank destroyers could ambush. But whatever the merits of the doctrine, it produced a fascinating engineering requirement. The Army wanted a fast, lightly armored, powerfully armed tracked vehicle, and it wanted it faster than any tracked vehicle had ever been. The requirement landed at Buick, and Buick built the Hellcat. This is the paradox at the center of the story. The fastest, most mobile, most mechanically sophisticated armored vehicle of the Second World War was built not by a tank company, not by a locomotive works, not by a heavy industry firm, but by Buick, the General Motors division that made comfortable, smooth, middle-class American automobiles. Buick knew nothing about tanks when the war began. What Buick knew about was making vehicles that rode smoothly, accelerated pleasantly, and were easy to drive, the qualities that sold cars to the American middle class. And it turned out that those qualities, translated into military terms, were exactly what a fast tank destroyer needed. The smooth ride became the steady gun platform. The easy driving became the rapid crew training. The automotive engineering of comfort became the military engineering of speed and mobility. The resolution of the paradox lies in the deep engineering that Buick and its sister GM divisions had developed for the civilian market, and specifically in two technologies, the torsion bar suspension and the automatic transmission. These were not military technologies, they were automotive technologies, developed to make passenger cars ride better and drive easier. But when Buick applied them to the tank destroyer, they produced a vehicle of extraordinary capability. The torsion bar suspension gave the Hellcat a ride smooth enough to allow accurate gunnery at speed and to let the vehicle cross rough ground at velocities that would have shaken a leaf-sprung tank to pieces. The automatic transmission let the Hellcat keep its engine in its power band and let its driver concentrate on the battlefield instead of on shifting gears. To understand the Hellcat, you have to understand these two technologies in detail, how they worked, why they mattered, and what made them special. That is the engineering that the patriotic histories skip, and it is the engineering that made the Hellcat the fastest armored vehicle of the war. The popular history of the Hellcat says that it was fast and that it had an automatic transmission, and then it moves on. It does not explain how the automatic transmission worked or why it was different from other automatic transmissions, or how a transmission could shift itself in 1943. It does not explain how the torsion bar suspension worked or why it gave a better ride than the systems on other tanks. It treats the Hellcat's mechanical sophistication as a kind of magic, something to be admired rather than understood. And a viewer of these stories was right to complain about exactly this tendency, the tendency to assert with great confidence that something worked, while never bothering to explain what made it special or how it actually functioned. So this account makes a promise, and the promise is to explain the mechanism. We will explain how the Torqmatic transmission shifted the Hellcat through its gears, what a torque converter is, and how it multiplies torque using nothing but moving fluid, why the Hellcat used a torque converter transmission while the Cadillac light tank used a different kind of automatic and what the difference was. We will explain how a torsion bar suspension works, how a steel bar twisting along its length can suspend a 20-ton vehicle and give it a smooth ride. We will explain how the Hellcat's engine and transmission could be slid out of the vehicle on rails for maintenance. The goal is not to tell you that the Hellcat worked. The goal is to show you how it worked in enough mechanical detail that you understand the engineering. Because the engineering is the whole point, and the engineering is what the usual histories leave out. The Hellcat began, surprisingly, in a styling studio. The vehicle that became the M18 originated in the design studio of Harley Earl, the legendary General Motors styling chief who is remembered as the father of American automotive design, the man who created the GM art and color section, who designed the tail fins and the chrome and the flowing bodies that defined American cars in the middle of the 20th century. Earl was the head of styling at GM, and his Buick division design team took on the tank destroyer project. This was itself remarkable, because previously the basic designs for military vehicles had originated within the Army's Ordnance Department, the government's own engineers. The Hellcat was different. It came from a General Motors design studio, conceived by the same organization that styled Buicks, and Earl's staff even designed the snarling Hellcat logo that appeared on the vehicle's front corner and on the patches worn by its crews. This origin matters because it shaped the whole character of the vehicle. The Hellcat was approached from the beginning as an automotive engineering problem rather than a traditional ordnance problem. It was designed by people who thought about vehicles the way the automobile industry thought about them, in terms of performance, ride quality, ease of operation, and manufacturability. It was tested the way Buick tested its cars, at the GM Milford Proving Ground, on the banked oval and over specially built stretches of bumps, the same facilities and methods that Buick used to develop its passenger cars. The Hellcat was, in a deep sense, a Buick, a product of automotive engineering culture applied to the problem of building a fast tank destroyer. and it benefited enormously from that automotive heritage, because the automobile industry had developed for its civilian products exactly the technologies, the smooth suspension and the self-shifting transmission that a fast-tracked vehicle needed. The Hellcat did not spring into existence fully formed. It was the endpoint of a long evolution of fast tank destroyer prototypes, each one changing as the Army revised its requirements. The story began in December of 1941, when the Ordnance Corps issued a requirement for a fast tank destroyer using the Wright Continental R975 engine and a 37mm gun, with a Christie suspension, the spring-based system used on some fast tanks of the era. This first concept was designated the T-42. Almost immediately, the requirements began to change. In April of 1942, the Army asked for the 37mm gun to be replaced with a more powerful 57mm gun, the British 6-pounder, and for the Christie suspension to be replaced with a torsion bar system. This became the T-49. Then the tank destroyer force decided it wanted still more firepower, the same 75mm gun used on the Sherman, and the second pilot was rebuilt with that gun as the T-67, delivered in November of 1942. The T-67 was promising, but testing revealed that a more powerful engine was needed, and meanwhile an even better gun had appeared, the 76mm gun being developed for the Sherman. So the T-67 project was closed in January of 1943, and the Ordnance Department directed that 6 pilot models of a new vehicle, the 76mm gun motor carriage T-70, be built, with torsion bar suspension, a more powerful engine, a new turret, and a revised hull. The T-70 was the Hellcat. The first T-70 pilot was delivered in April of 1943, and all 6 were completed by July. After testing and refinement, the T-70 was standardized in March of 1944 as the 76mm gun motor carriage M18. The long evolution from the 37mm T-42 through the 57mm T-49 and the 75mm T-67 to the 76mm T-70 reflected the Army's steadily rising demands for firepower, and it produced, at the end, a mature and well-developed vehicle. Now we come to the engineering, and we start with the suspension, because the suspension was one of the 2 keys to the Hellcat's performance. The Hellcat used a torsion bar suspension, and to understand why this mattered, you have to understand what a torsion bar is and how it works, because it is genuinely clever. A torsion bar is, quite simply, a long steel rod. One end of the rod is anchored rigidly to the hull of the vehicle. The other end is attached to a road wheel arm, the pivoting arm that holds one of the vehicle's road wheels. When the road wheel hits a bump and rises, it rotates the road wheel arm, and because the arm is attached to the end of the steel rod, it twists the rod along its length. The steel rod resists being twisted, and that resistance is the springing force of the suspension. The rod acts as a spring not by compressing like a coil spring or bending like a leaf spring, but by twisting along its length. The beauty of this arrangement is several-fold. A steel rod twisting along its entire length can store a great deal of energy smoothly and progressively, giving a supple, controlled ride. Because the torsion bars run transversely across the bottom of the hull underneath the crew compartment, they take up very little vertical space, allowing the vehicle to be built lower than one using tall coil springs, and a lower vehicle is a smaller target and has a lower center of gravity. The torsion bars are protected inside the hull, where enemy fire and debris cannot easily damage them, and the system provides a long wheel travel, letting the road wheels move up and down a great distance to follow rough ground, which is exactly what allows a vehicle to cross broken terrain at high speed without the hull pitching and bucking. The Hellcat's torsion bar suspension, with 5 road wheels on each side, each on its own twisting bar, gave the vehicle a ride steady enough to allow it to move fast over rough ground, and crucially, steady enough to give the gunner a stable platform. This was the automotive engineering of ride quality applied to a tank destroyer, and it was a large part of why the Hellcat could actually use its tremendous speed in the field rather than just on a smooth test track. The Hellcat's power came from the Continental R975, the 9-cylinder air-cooled radial aircraft engine, the same basic engine that powered many Shermans. This is worth pausing on because it is a small irony. The radial engine, which was a compromise and a problem in the Sherman, Too tall, air-cooled, originally designed for airplanes, was a reasonable choice in the Hellcat because the Hellcat was designed around it from the start rather than having it forced in as a substitute. The R975 was a 9-cylinder radial, its cylinders arranged in a circle like the spokes of a wheel, displacing about 973 cubic inches, and in its tank form, it produced somewhere between 350 and 460 horsepower, depending on the variant and the tune. The early Hellcats used the naturally aspirated R975C1, producing around 350 horsepower, and later ones used the improved R975C4, producing around 400 horsepower or more. The engine was mounted in the rear of the vehicle, which is the natural place for a tank engine, close to the rear-mounted final drive. But the Hellcat's drivetrain layout had an unusual feature. The engine was in the rear, but the transmission was in the front, driving the front sprockets, with a drive shaft running the length of the vehicle to connect them. This front drive layout was common in American tanks of the era, and it had advantages in weight distribution and in the placement of the drive sprockets. But it meant that a long drive shaft ran under the fighting compartment from the rear engine to the front transmission. The combination of the rear radial engine, the front transmission, and the connecting drive shaft was the basic power layout of the Hellcat. And the transmission, mounted up front, was the second of the two technologies that made the Hellcat special, and the one that the viewer most wanted explained. So let us explain it properly. Before we can explain the Hellcat's transmission, we have to explain the torque converter. Because the torque converter is the heart of the whole thing and the key to how the transmission could work without a clutch. Imagine two electric fans facing each other. Turn one fan on, and the moving air it blows will start to spin the blades of the second fan, even though the two fans are not physically connected. The first fan, the one driven by the motor, transmits power to the second fan through nothing but the moving air between them. A torque converter works on exactly this principle, but using oil instead of air, and inside a sealed housing. There is a pump, called the impeller, connected to the engine, which spins and flings oil outward by centrifugal force. Facing it is a turbine connected to the transmission, which the flung oil strikes and drives, making it spin. The engine spins the impeller flings oil at the turbine, the oil spins the turbine, and the turbine drives the transmission. Power is transmitted from engine to transmission through moving fluid with no solid mechanical connection, which means the engine can keep running while the vehicle is stopped, with the oil simply churning, no clutch required. But a torque converter does something more than a simple fluid coupling. This is the clever part. Between the impeller and the turbine sits a third element, a stationary set of curved vanes called the stator. After the oil has passed through the turbine and given up its energy, it is moving in the wrong direction, and if it simply flowed back to the impeller, it would fight against the impeller's rotation and waste energy. The stator catches this returning oil and redirects it, turning it around so that it flows back into the impeller in the direction that helps the impeller rather than hindering it. This redirection does something remarkable. It multiplies torque. The torque coming out of the turbine is greater than the torque going into the impeller because the stator recovers the energy of the returning fluid and feeds it back in. A torque converter is therefore not just a fluid clutch, it is a torque multiplier, a device that increases the twisting force from the engine, most powerfully when the vehicle is starting from a stop and the difference in speed between the impeller and turbine is greatest. This is why a torque converter gives such smooth, strong acceleration from rest. The fluid both connects the engine smoothly and multiplies its torque exactly when the torque is most needed. Now we can explain the Hellcat's actual transmission, the Torqmatic 900T, and what made it special, and why it was different from the automatic transmission in the Cadillac-powered M5 light tank. This is the distinction that matters, and it is the distinction the popular histories never make. The M5 Stewart used the hydromatic transmission, which was a fluid coupling combined with planetary gears. A fluid coupling is the two fans facing each other arrangement, with an impeller and a turbine but no stator, so it transmits power smoothly but does not multiply torque. The Hydromatic worked beautifully behind the modest Cadillac car engines of the light tank, but it could not have survived behind the big radial engine of the Hellcat. The Hellcat's radial produced enormous torque, on the order of 940 pound-feet, and that much torque fed through a simple fluid coupling and the relatively delicate Hydromatic gearing would have, in the vivid phrase of one engineering history, made an oily metal milkshake of the transmission's innards. The Hellcat needed something far more robust and something that could multiply torque rather than just transmit it. The answer was the Torqmatic 900T, a heavy-duty torque converter transmission designed by Oliver K. Kelly, one of the principal architects of the Hydromatic, and built by GM's Allison division. The Torqmatic combined a torque converter with two hydraulically controlled planetary gear sets, giving 3 forward speeds and 1 reverse. And its torque converter was not a simple 3-element unit, but an elaborate 6-element converter with a single impeller, 3 turbines, and 2 stators, all working together to give a wide range of torque multiplication. The stall ratio of this converter alone was 4.8 to 1, meaning that when the vehicle was starting from a stop, the converter multiplied the engine's torque by nearly 5 times before the gearing even got involved. This is what gave the Hellcat its tremendous acceleration. The combination of the torque-multiplying converter and the 3-speed planetary gearbox kept the radial engine within its narrow, effective power band all the way up to the Hellcat's top speed, and it had the strength to handle the radial's monstrous torque without destroying itself. The Torqmatic was not a luxury car transmission pressed into military service. It was a purpose-built, heavy-duty automatic designed from the start to handle the punishment of a fast, heavy, hard-driven armored vehicle. To complete the picture of how the transmission worked, we have to explain the planetary gear sets, because the torque converter alone could not provide all the gear ratios the vehicle needed. The torque converter multiplied torque smoothly, but only over a limited range, and to give the vehicle a proper set of gears, from a low gear for starting and climbing to a high gear for road speed, the transmission needed actual gear sets behind the converter. These were planetary gear sets, and the planetary gear set is one of the most elegant pieces of mechanical engineering ever devised. A planetary gear set consists of a central gear called the sun gear, a set of smaller gears called planet gears that surround and mesh with the sun gear, held in a frame called the planet carrier, and an outer ring with internal teeth called the ring gear, or annulus, which meshes with the planet gears from the outside. The planets orbit the sun like the planets of the solar system, which is where the name comes from. The beauty of the planetary gear set is that it can produce different gear ratios depending on which of its elements is held stationary and which is driven. If you drive the sun gear and hold the ring gear stationary, the planet carrier turns slowly, giving a reduction in speed and an increase in torque, a low gear. If you drive different elements or lock different ones, you get different ratios, including direct drive and reverse. The transmission controlled which elements were held and which were driven by means of hydraulically operated clutches and brake bands, friction devices that could grip and release the various gear set elements under the control of hydraulic pressure. By engaging and releasing these clutches and bands in the right combinations, the transmission could select its 3 forward gears and its reverse, shifting from one ratio to another by changing which elements of the planetary sets were locked. The shifts happened by hydraulic control, smoothly without the driver operating a clutch. In the Hellcat, the 3 forward gears gave ranges of roughly up to 16 miles per hour in first, 12 to 34 in second, and 30 to 60 in third, with the engine governed so that the vehicle would normally top out around 55. The driver selected the range, but within the operation, the torque converter and the planetary gears did the work of multiplying and transmitting the power smoothly, with no clutch pedal and little chance of a missed shift. One more piece of the Hellcat's engineering deserves explanation, because it shows the depth of thought that went into the vehicle, and that is the maintenance system. A tank engine and transmission need regular maintenance and sometimes complete replacement, and getting at them buried inside an armored hull is normally a slow and laborious job, requiring cranes and hours of labor. The Hellcat's designers, thinking like automotive engineers who cared about serviceability, built in a remarkable solution. The engine and the transmission were mounted on rails. To service the transmission, the crew removed a large access plate on the front of the hull, disconnected the transmission from the drive shaft, attached extension rails to the mounting, and slid the entire transmission assembly straight out the front of the vehicle on the rails. To get at the bottom of the engine could be slid out the rear of the hull on a rail system integrated with the rear access door, without having to lift it out entirely. This rail system was a genuine innovation in armored vehicle maintenance, and it reflected the automotive industry's obsession with serviceability, the same thinking that designed cars so that mechanics could get at their components efficiently. It meant that a Hellcat with a damaged transmission or a failing engine could be repaired far faster than a conventional tank. The major components slid out, serviced or replaced, and slid back in. In the field, where a vehicle returned to service quickly is worth far more than one that sits in a repair depot for days, this was a real advantage. It was the kind of detail that the Ordnance Department's traditional designers might not have prioritized, but that the automotive engineers at Buick, steeped in the culture of mass production and field service, built in as a matter of course. The rails were not glamorous, but they were a real piece of engineering intelligence, and they made the Hellcat a more practical weapon. All of this engineering, the torsion bars, the torque converter transmission, the radial engine, served a single tactical idea, that speed could substitute for armor. The Hellcat carried almost no armor by the standards of a tank. Its frontal armor was about 1 inch thick, its turret armor in places as little as a 1/4 inch, and its turret was open at the top, roofless, to save weight. A Hellcat could be penetrated by almost any anti-tank weapon that hit it, including weapons that a Sherman or a German tank would shrug off. By the logic of conventional armored warfare, this was suicidal, but the Hellcat was not meant to fight by the logic of conventional armored warfare. It was meant to fight by speed. The crews learned to use the Hellcat's tremendous speed and acceleration to fight in a way no other armored vehicle could. They would use the vehicle's mobility to reach a firing position before the enemy expected them, fire a few quick rounds from their accurate 76mm gun, and then use the Hellcat's acceleration to displace, to dart away to a new position before the enemy could return effective fire. The vehicle's speed let it appear, strike, and vanish. It could outrun the traverse of an enemy tank's turret. It could relocate faster than the enemy could reorient. In the hands of a skilled crew, the Hellcat was a hit-and-run ambush predator, exactly as the tank destroyer doctrine had envisioned, surviving not by absorbing hits, but by never being where the enemy's guns were pointed. The speed that the torsion bars and the Torqmatic transmission and the radial engine had given the vehicle was, in combat, its armor. When the Hellcat fought the way it was designed to fight, using its speed, it was devastatingly effective. The most famous example came at the Battle of Aracourt in September of 1944, where Hellcats of the 704th Tank Destroyer Battalion, fighting in fog that masked their thin armor, used their mobility to ambush and destroy large numbers of German Panther tanks for minimal losses, one of the most lopsided armored actions of the war. The Hellcat compiled a remarkable combat record. It is often credited with achieving the highest kill-to-loss ratio of any American armored vehicle of the war, with figures around 8 enemy vehicles destroyed for each Hellcat lost frequently cited. By the measure of enemy tanks killed versus Hellcats lost, the vehicle was the most effective American tank destroyer of the war. When a Hellcat crew could fight on their own terms, using speed and ambush and the accurate 76mm gun, they were extraordinarily lethal, and the kill ratio reflects how well the vehicle performed in the role it was designed for. But an honest account has to note the larger problem, which was not with the Hellcat, but with the doctrine that produced it. The tank destroyer concept, the idea of defeating enemy armor with fast, lightly armored specialist vehicles held in reserve, turned out to be largely mistaken. Enemy tanks did not oblige by attacking in the neat, massed thrusts that the tank destroyers were designed to ambush. Most of the time, the tank destroyers ended up being used like regular tanks, supporting infantry, providing direct fire, doing the everyday work of armor. And in that role, their thin armor and open turrets were a serious liability. The whole tank destroyer branch was disbanded shortly after the war, its doctrine judged a failure. The Hellcat was a brilliant solution to a problem that, in the end, did not exist in the form the Army had imagined. It was the best possible vehicle for a flawed concept. This does not diminish the engineering achievement, but it places it in context. The Hellcat was magnificently engineered and genuinely effective in its designed role, and the role itself was based on a doctrine that the war proved wrong. Both things are true, and the honest story includes both. The Hellcat went into production at the Buick plant in Flint, Michigan in July of 1943, and production continued until October of 1944. Buick had originally been contracted to build a far larger number, but the changing fortunes of the tank destroyer doctrine and shifting Army priorities cut the order back, and in the end, 2,507 Hellcats were built. This was a modest number compared to the nearly 50,000 Shermans, reflecting the specialized and limited role of the tank destroyer, but it was enough to equip many tank destroyer battalions and to make the Hellcat a significant presence on the battlefields of Europe. The Hellcat first saw combat at Anzio in Italy in May of 1944 and went on to serve primarily in the European theater after the Normandy landings, with smaller numbers in Italy and the Pacific. It served through the rest of the war in Europe, including in the desperate defensive fighting of the Battle of the Bulge, where its mobility was valuable in the fluid, fast-changing situation. The vehicle's chassis also served as the basis for the M39 Armored Utility Vehicle, a turretless version used to carry personnel and cargo and to tow guns, which served in the war and in Korea. The Torqmatic transmission that powered the Hellcat went on to a long career as well, both in the M26 Pershing heavy tank that appeared at the end of the war and after the war as the basis for an extensive line of Allison heavy-duty torque converters from military, commercial, and industrial use. The transmission that Buick and Allison had developed for the fastest tank destroyer of the war became, in its descendants, a workhorse of heavy vehicles for decades. There is a direct and fascinating line from the Hellcat's transmission to the post-war American automobile, and it closes the circle of this story. After the war, Buick took the torque converter transmission technology it had developed and refined for the Hellcat and the principles behind it, and it turned that technology into a civilian automatic transmission, the Dynaflow, introduced for the 1948 model year. The Dynaflow was based on the same fundamental principles as the Torqmatic, a multi-element torque converter combined with planetary gears. Like the Torqmatic, the Dynaflow used a torque converter to multiply torque and transmit power smoothly without a clutch, and it gave Buick automobiles a famously smooth, seamless acceleration, free of the shift shock that characterized other automatic transmissions of the era. The Dynaflow was, in a sense, the Hellcat's transmission tamed and refined for the comfort of civilian Buick buyers. The technology that had been developed to handle the monstrous torque of a radial-engined tank destroyer and to give it smooth, clutchless acceleration on the battlefield became, a few years later, the technology that gave a Buick Roadmaster its smooth, clutchless acceleration on the boulevard. There was an irony in it, and a kind of poetry. The same engineering principles, the torque converter and the planetary gears, served the snarling Hellcat seeking out German Panthers and the comfortable Buick carrying a family to church. The military requirement had driven the development, and the civilian market had inherited the result. This is a recurring pattern in the history of technology, the military application that advances a technology which then flows into civilian life, and the Hellcat to Dynaflow line is one of the cleanest examples of it. The fastest armored vehicle of the war fathered the smoothest luxury car transmission of the post-war decade. The lesson of the Hellcat is a lesson about what the automobile industry brought to the war, which was not just manufacturing capacity, but a whole engineering culture. The Hellcat was designed in a styling studio by people who thought about vehicles the way the automobile industry thought about them, and it was tested like a passenger car at an automotive proving ground. And it was a better vehicle for that automotive heritage. The torsion bar suspension that gave it a smooth, fast ride, the automatic transmission that let its driver concentrate on combat, the rail system that made it easy to service, all of these were the fruits of automotive engineering, of an industry that had spent decades learning to make vehicles that rode well, drove easily, and could be serviced and mass-produced efficiently. This was the deeper American advantage in the war, deeper even than the sheer scale of production. The American automobile industry possessed an engineering culture oriented toward performance, refinement, ease of use, and manufacturability. And when that culture was turned to the design of military vehicles, it produced weapons that were not just numerous, but genuinely sophisticated in ways that mattered. The Hellcat was faster, smoother riding, easier to drive, and easier to maintain than vehicles designed by traditional military engineering, because it was designed by people who had spent their careers solving exactly those problems for the civilian market. The Germans built tanks with a tradition of heavy engineering and military specialization. The Americans built the Hellcat with a tradition of automotive engineering and mass-market refinement. And the automotive approach, applied to the specialized problem of the fast tank destroyer, produced the fastest and in many ways the most advanced armored vehicle of the war. The lesson is that engineering culture matters, that the habits and values an industry develops in one domain can transfer powerfully to another, and that the American automobile industry's civilian engineering culture was one of the secret weapons of the American war effort. In a war decided by what worked was a tank destroyer designed in a car styling studio, suspended on twisting steel rods and driven through a transmission that shifted itself by churning oil through a 6-element torque converter. The Hellcat was fast, the fastest tracked armored vehicle of the war, faster than the M1 Abrams that would follow it 4 decades later. But to say it was fast and stop there, as the usual histories do, is to miss the whole point. The Hellcat was fast because of specific engineering, because Buick's engineers gave it a torsion bar suspension whose twisting steel rods let it cross rough ground at speed without shaking itself or its crew to pieces, and because they gave it a Torqmatic torque converter transmission whose churning fluid multiplied the radial engine's torque nearly 5-to-1 off the line and shifted the vehicle through its gears with no clutch and no missed shifts and no danger of grinding the gearbox into an oily metal milkshake. The engineering came from the automobile industry, from the same Buick that built smooth, easy, comfortable cars for the American middle class, designed in Harley Earl's styling studio and tested on the same banked oval at Milford where Buick wound out its sedans. The torque converter that drove the Hellcat into battle against German Panthers became 3 years later the Dynaflow that gave Buick Roadmasters their famous boulevard smoothness. The torsion bars that let the Hellcat ambush and vanish became standard suspension technology for armored vehicles for generations. The automotive engineering of comfort and ease, translated into military terms, became the engineering of speed and lethality, and the Hellcat was the proof. In a war fought between industrial cultures, the culture that could take its expertise in making cars ride smoothly and drive easily and turn that expertise into the fastest armored vehicle on Earth was a culture its enemies could not match. The tank destroyer doctrine that produced the Hellcat was flawed, and the branch was disbanded after the war, and the Hellcat was in that sense the perfect answer to the wrong question. But the engineering was real, and it was brilliant, and it deserves to be understood and not just admired. The Hellcat did not run on patriotism or on the assertion that it worked. It ran on torsion bars and torque converters and planetary gears, on specific, knowable, explicable engineering, designed by people who knew how to make a vehicle go. That is the engineering, and the engineering is the point. The Hellcat worked because Buick built it to work, and now you know how. That was enough. It was, in the end, the fastest thing on tracks in the entire war, and it acted that way not by magic, but by mechanism.